we got the efflux velocity as under root 2gh divided by 1 minus AO square by AS square. If we assume that the area of cross section of the orifice is very less than AS, or the surface area, which is, let's say the surface is a very large surface, a container has a very large cross sectional area, and we have a very small orifice at the bottom of it, something of this sort. If we have something like this, then we have this ratio AO by AS being very less than 1. If this quantity is very less than 1, this will imply that this quantity, the square of it, will be very less than 1. Because this quantity is very small, we can kind of ignore this quantity or neglect this quantity here. So what we are left with is only this. So the velocity of efflux becomes root over 2gh. Now make an analogy of this with a small point mass falling freely from a height h. When we apply energy conservation like this in outside, let's say in our normal mechanics problems, what we say is when this small point mass falls through a height of h freely, at the end of this height h, it attains a velocity of root 2gh. Same thing is happening here. We now can say that the fluid, given this, the fluid has fallen freely through a height h. This is known as Torricelli's law. So in general, whenever a problem holding that a container with a top cross sectional area very large than the cross sectional area of the orifice is given, we can always apply Torricelli's law and say that the velocity of efflux through that orifice is going to be basically root 2gh, where small h is the height between the surface and the orifice. Let us now look at a few problems based on Bernoulli's principle. See, we have a container like this with a small orifice in the bottom. We have two liquids separated by this interface. Say this is liquid 2 of rho 2 and another liquid on the top of it. Let's say this has a density of rho 1. The cross-sectional area of this small orifice is, let's say, AO. The surface cross-sectional area is, say, AS. And we are assuming that this is very less than AS. This height is H1. This height is, say, H2. Because this is stated, we can say that Torricelli's law is valid. Our objective is find the efflux velocity. what we will do here is apply Bernoulli's equation between 2 points. Now, what points are going to be those? Are they going to be these points? Are they going to be these points? Or what? If we choose a point here and a point here, then obviously we cannot apply Bernoulli's equation, because this is a situation where there are two liquids. So the streamline, whatever path this fluid particle will take through this, will have to be traveling through two liquids. Thus Bernoulli's equation cannot be applied between these 2 points. So let's say we apply Bernoulli's equation between this point and this point. So if we apply Bernoulli's equation between these 2 points, we get the pressure energy as atmospheric pressure, plus we are considering the point here, say, so the pressure here will be the pressure due to this fluid height of H1. So rho 1 G capital H1, this is the pressure term, plus the kinetic energy. Because this is at the cross-sectional area AS and this condition is holding, we can say that the velocity here is very small or negligible compared to the velocity here. So the kinetic energy part goes to 0. The potential energy term, say our reference is somewhere here along this line, let's say this is our origin, then the point here is at a height h2. So we will have a term of rho 1 G, sorry, this is going to be rho 2 G H 2. So this is because of the potential energy. This has to be equal to these quantities at this point. So the pressure energy will be PATM only plus half rho 2 V2 square, or let's say VE square. We have to find the efflux velocity. This is the kinetic energy term, and the potential energy will be 0. If we now simplify this equation, what we will get is half rho 2 VE square being equal to rho 1 GH1 plus rho 2 GH2. Simplifying this further, VE square is equal to 2 times G rho 1 by rho 2. We have brought this rho 2 here, the 2 here. So rho 1 by rho 2 H1 plus this will be divided and cancelled off, so only H2. So this is VE square. So now when we write the expression for efflux velocity, that is going to be, this is followed here. So VE is going to be under root 2G into rho 1 by rho 2 H1 plus H2. So this is our efflux velocity. Here the problem is solved. Let us now define some things for further problems on, if we face some problems of this format, how we can generalize this equation for those problems also. This term here, this is known as equivalent height of fluid 1 with respect to 2. This is something which can be generalized for a lot of fluids. Say we have multiple layers of fluids going one after the other. We have rho 2, then let's say we have rho n minus 1, rho n minus 2, rho n minus 3, up to, let's say, rho 0, we have n such fluids, we can generalize this concept for those many fluids. How can we do that? Let us see.